Okay, so welcome back to this Symmetric Cryptanalysis session. We have two talks later. And the first one is differential multivariate cryptanalysis, which is Christine André, Nicolas David, Patrick Verbès, and Patrick is giving
So this work started on the simple question. Can we use meet in the middle related techniques to improve differential attacks? Or more generally, can we combine meet in the middle attacks and differential attacks into a more powerful cryptanalysis technique? In this talk, I will begin by recalling how differential attacks and meet in the middle attacks work. And then I will present the new framework answering this question, and as well as the results we obtain. So differential attacks. The core of the differential attack is a differential distinguisher, which is a pair of input and output differences for which the transition occurs more, the probability of the transition is higher than what we would expect for a random permutation. Then this differential distinguisher is extended into key recovery attacks by happening few rounds at the beginning and at the end of the distinguisher. And given a pair of data, of messages, the goal is to partially encrypt and decrypt the pair to obtain the differences at the input and output of the distinguisher. And the main idea is that if given n of pairs of data, the right values of the key material involved in the partial encryption-decryption process should appear more often than the wrong ones, and so we can identify it. So the critical part of differential attack is, given a pair of data, how we can determine the possible values for the key material involved in the encryption-decryption process. This part is not trivial, and it is usually done by applying a ribbon-like procedure in which we will propagate the differences from both sides, and we will rely a lot on the fact that if we know the inputs and the output differences of an S-box, we can compute the possible values of this S-box. And then if we have the values around the key addition, we obtain the values of the key. But finding the right order in which propagating differences can be a bit tricky if the key bits involved in this process are related to each other, or for ciphers for which the key addition is partial. And the fact is, if we have S solutions for the key bits, we would like to enumerate all the S solution in the time complexity around S operations. Otherwise, it will increase the time complexity of the differential attack. And so we want to not increase the time complexity of the attack. And it's not always possible to enumerate this S solution into with S operation. So that's all for the differential attack. And now let's talk about meet in the middle attack. The most famous example of meet in the middle attack is against double DES, and more generally against any cipher constructed as the successive applications of two independent ciphers. Against such a construction, we can apply a generic attack consisting in computing the middle states from both ways independently and looking for collisions. So how it works? First, we initialize a hash table, an empty hash table, in which we will store the middle state and the corresponding key values. Okay. So first, we loop on all possible values for K1, partially encrypt the plain text to compute the middle state, and we store the values of the middle state on the hash table together with the corresponding values of K1. Then, once it's done, we do the same thing on the ciphertext. So we loop on K2, partially decrypt the ciphertext, obtain the value of the middle state, and then we look into the hash table for possible matches. And if we get the matches, we will retrieve the corresponding value of K1. So we obtain the possible values for K1 and K2. This generic attack allows to attack this cipher, which has a security of 2K bits, and it reduce the security to a K bits only. So of course, this is only a very simple example of meet-in-the-middle attack. And in practice, we can mount much more sophisticated meet-in-the-middle attacks, as for instance, this one from Donget Hall, which was presented at Crypto 2 years ago. So this is a meet-in-the-middle attack against Skinny 128.384 against 23 rounds of and so you don't have to understand this figure. But here you can compute the values of the blue bytes and of the red bytes independently, and then look for matches between some linear equations involving both those things. I think this attack is very interesting. So can we combine both differential attacks and meet-in-the-middle attacks? Of course, the answer is yes. And actually, this was done many times in many attacks. And for instance, for many meet-in-the-middle attacks, it's common to assume that the difference on some bytes or nibbles, I don't know, is 0. Because in this case, some differences, some values will have less possibilities, okay, and it reduces the complexity of them. Also, the differential enumeration technique is a technique which was proposed by Dunkelman, Keller, and Shamir to improve a particular kind of meet-in-the-middle attack. And in this technique, we use a truncated differential characteristic to reduce the complexity of this meet-in-the-middle attack. The common points of all those attacks, combining differential and meet-in-the-middle, is that they are all meet-in-the-middle attacks for which we reduce some part of the complexity, so the time complexity or the memory complexity, by using truncated differential. And this is where our work is new, because we don't start from a meet-in-the-middle attack. We start from a differential distinguisher. And the idea is to use a technique like meet-in-the-middle attacks to turn this distinguisher into a key recovery attack. Okay, so it's really a differential distinguisher that we will extend into a key recovery attack using meet-in-the-middle related techniques. So how it works? Instead of having a lot of pairs and then searching for the right values for K in and K out, we will generate the pairs using by looking for collisions. So first we ask for one plaintext ciphertext pair, PC, okay. And then we will loop over all the possible values of K in, partially encrypt this plaintext, apply the difference of the input difference of the distinguisher, partially decrypt this new states to obtain a new plaintext key prime. And we store this P prime. Well, yes, we store P prime in a hash table together with the value of K in used to compute it. Okay. We do the same for the ciphertext. Okay, so we start from C. We look on all the possible values of K out. We apply the output difference of the distinguisher, and we partially encrypt this new set, this new state, to obtain C prime. And this C prime, we ask for the corresponding plain text of this C prime, and we look if this plain text belongs to the hash table we built in the first step. Okay. So here, the meet in the middle procedure is used to search pairs P prime, C prime that are valid plain text ciphertext. Okay. So it's different than classical differential attacks, because here we generate the pairs used for the attack. And if we want to compare, so we call this new framework differential meet in the middle attack. And if we want to compare it to a classical differential attack, so first, it will probably require more memory. Okay. Attacks, differential meet in the middle attacks will require more memory than classical differential attacks, because for differential attacks, you usually generate all the pairs you need on the fly. Okay. You just have the data, and then you look for collision on the data, or shear match to the data, and you can generate all the pairs you need on fly. While here, we somehow need to store all the pairs we will need to perform here. So more memory. But on the other hand, it is much easier to deal with the key, okay, because it's much easier to look on K in and compute P prime than given P and P prime, find the right values of K. This the problem is much simpler. So for this we win, and we hope that in certain circumstances we will have a better time complexity than for classical differential. And there is also a specific improvement for ciphers with partial key addition, which allows us to add an extra pre-round to the attack. And this is, I think, the most important advantage of this new framework to extend the differential distribution. And I will talk about it later. So we applied this new cryptanalysis technique against two ciphers, so Skinny and AES. And for both those ciphers, we obtained new results against the largest version of both of them. So first, for Skinny 128.384, we obtained the first attack against 25 rounds in the single key model, which is 2 more rounds than the previous best new attack. And for AES 256, we obtained the first attack against 12 rounds in the related key model, which only requires 2 related keys. Because you may know that there is an attack, a related key attacks against full AES 256, which is a boomerang attack, but it requires 4 related keys. And if you restrict the number of possible allowed related keys to 2, that's the best known attacks. And the previous best one was really 10. We tried to apply this this framework and this cryptanalysis technique to the other versions of the ciphers, and actually we did not find any interesting results. So it seems that differential meet in the middle attacks works well, or at least better, when the key size is much larger than the block size. Let's see the restriction of this new family. So here you can see in more details the results we obtained against skinny 128, 384. So as you can see, the gain over the generic bound of exhaustive search is non-marginal, and the complexity, the time complexity of our attack against 25 rounds is smaller than the best known attacks against 23 rounds. So we believe it's very nice improvements. And I will explain now how this 25 attacks, this 25 rounds attacks works. So first, we found a new differential over 15 rounds for skinny 128. And so you have the picture of the differential here. And we used a tool, a modified version of the tool I worked on and with my co-authors at in a work published at ACNS in 2021. And we obtained that the probability of this differential is higher than 2 to the minus 160.5. So that's the starting point of our attack. And then we extend this distinguisher by adding 4 rounds to the plain text, 5 to the ciphertext, and 1 extra. Before explaining the extra 3 rounds, a note on a remark on the data complexity. So if you extend the distinguisher by 4 rounds to the plain text, you can see that the plain text is fully active. Okay, so if you naively apply our framework to attack that, you will need the full code. So to avoid that and to reduce the data complexity, we propose to force some values in the plain text. Okay, so basically we have a limited amount of plain text available, and we want to generate only plain text in this data available. So if you do that naively, you will increase the time complexity, okay, because whenever you will generate a plain text that is not in the data you have, you will have to start. But and if you don't want to increase the time complexity, basically you have a procedure which is very similar to classical differential attack, because you have the difference here, and you need to generate the possible values of the key material. Okay. It is still different because here you only work on the upper part and on the lower part independently. But I think the argument about how easy it is to compute the plain text and the keys and so on vanishes. It can be a bit complicated, but it works. So now let's talk about the extra 3 rounds. If you so this is 1 round of skinny, and for skinny, the key is only applied on the 2 first rows. And the idea is to instead of performing the attack from 1 plain text ciphertext pair, we will perform the attack for a structure of 2 to the 64 plain text ciphertext. Okay, because if we have the structure of 2 to the 64 plain text, so here we have all the possible values. Okay, here we pick some constant, and here this part takes all 2 to the 64 values. And before the key addition, it will be exactly the same in a different order, but we have the exact same structure. All the possible values here and 1 constant here. Okay, so we can apply the attack for the 2 to the 64 messages in parallel, and that's why it does not increase the complexity. Because when I presented the framework, I forgot to mention that, of course, this procedure has to be repeated many times, so precisely 2 to the p times, okay, which is, and 2 to the minus p is the probability of the differential distribution. And if you want to do that for the whole structure in parallel, you just have to repeat it to the p minus 64 times, and you will work for the whole structure at the same time. And now, instead of looking only for the p prime, c primes that are valid, you will look for the p, c, and p prime, c prime that are valid. But you can still do that by looking for collision. And for skinny, as the key schedule is linear, you have you can match on the full state, and it does not change the complexity of the partial attack. So it's really free. Because p is much higher than c. So I think this is really important and really specific to differential meeting the middle attacks, because I don't know how we would add an extra round for free for classical differential attacks. To conclude this talk, so I think we obtained very good results on especially the one on skinny 128.384. I don't know if it is a brand new cryptanalysis technique or only an alternative way of performing the key recovery part of the differential attack. I think it can be very interesting to understand when this cryptanalysis technique gives better results than classical differential attacks, and if it is possible to add more free round or to add an extra free round even for ciphers with a full key addition. Thank you for that.
We have some time for questions, either in the room or on Zoom. You can ask them in the chat. Okay, any questions from the audience so far? Well, I have one question. So you used proper differential in your attack, but do you think it can be extended to a truncated differential, which is mostly what it's also very common.
I think it's possible, and I'm not for sure that Maria is working on it. I think it's possible.
Okay. And no wishes, yes.
So I'm probably the answer here is we'll read the paper, but you talked about the memory requirements here. It seems like the collision search, you should be able to do nice parallel collision search stuff, time memory trade-offs to get the
Yes,
more efficient, right?
So yes, we will do intelligent stuff for the collision search. It's not the problem, but the thing is, we will at the end we still have to store all the pairs we will obtain. While this is not what we do for our classical differential. That's the only difference.
So you can't just store like the ends of some computation chains and then just determine if you made the collision by seeing if they match. The thing of the standard parallel collision search thing. I'm just
no, because yeah, we will generate all the possible P prime, C prime, okay, and they will all be stored somewhere. Okay,
right.
While for classical differential, you don't really store them because you have one data, you have a lot of collection of plain text, and you just put them in some hash table to look for collisions to generate the words. I see.
Yeah.
So okay, maybe it was not very clear, but I'm sure it requires more memory than classical app. And still, because so at least we will have to store all the P prime or all the C prime. Okay. And that's not something you do for classical. For instance, for skinny, for the attack on skinny, it's K out and K in are very high. You have to store a lot of plain text or a lot of stuff.
Okay. Thanks. Thanks to Peter again. And we move on to the next talk, which will be given in Zoom.
Okay.
So, where we set it up, this paper is entitled "Moving the Step of Cha-Cha in Syncopated Rhythm." It's a work by Shisheng Wang, Meicheng Liu, Shiki Hu, and Ngai Bin, and Chichang is giving the talk.
Okay, can you hear me?
Yes.
Can you see the slide? Okay, thanks, Chair, for your introduction. Good morning, everyone. My name is Shisheng Wang. It's my pleasure to be here to share our work with you all. This is a joint work with Meicheng Liu, Shiqi Hou, and Dong Dailin, which is on the security analysis of stream cipher Cha-Cha. Next, let's go straight to it. Here is an outline of this talk consisting of 3 parts: brief introduction, previous analysis of Cha-Cha, and our new attacks. Firstly, it's an introduction. AX-based design is an important branch in symmetric key cryptography due to its efficiency in implementation, especially in software aspect. It also provides good security properties. Today, there are many well-known cipher which adopt AX design, for example, block cipher, field, spike, stream cipher, SASA, Cha-Cha, and hash function, Blake, skin, authenticated encryption, the spike family, and McCluskey. We focus on the stream cipher Cha-Cha, which is designed by Bernstein in 2008. It is a variant of SASA to improve diffusion and used in Blake. In general, Cha-Cha take 256 bits key and 64 bits nonce, and the block counter as inputs and outputs 64 bytes of key stream. Cha-Cha, along with Poly 1305, is adopted in TLS, also in other protocols such as IPv2, IPsec, and SSH, and so on. Apart from the usage of encryption, Cha-Cha also being used as a procedure random number generator in the operating system with a Linux kernel. In a nutshell, Cha-Cha is one of the most widely used cipher in practice. Secondly, it's a previous analysis of Cha-Cha. At IFZ 2008, Amundsen et al. Proposed a significant improvement on the differential cryptanalysis of both SASA and Cha-Cha by introducing a new concept called probabilistic neutral bits, shortcut pin bits. This is the first key recovery key attack on 7 rounds of Cha-Cha. In general, the attack is launched by a meta-middle approach. For forward direction attacks, apply some input difference called ID for short to the initial state, and also output difference after certain rounds. For backward direction, to access the middle state at OD by inverting some round attacks, identify a set of key bits with left influence on output difference. That is the pin bits. And the attack compute output difference with ignoring the pin bits in online feeds. The most known attacks on SASA and Cha-Cha follow this framework, which is illustrated by this figure. To attack the capital R rounds of Cha-Cha, forward differential distinguisher of small r rounds is used with a correlation epsilon d. Then the attack need to invert capital R minus small r rounds to get access the state at OD from the key stream Z. And this progress is dominated by data if, which data means it is on to initialization. By the method PNB method, the attacks find the approximation data G whose variables are only on non-PNBs, which are labeled by green in this figure. In general, data G is constructed by restricting PNBs into fixed values. There are several future enhancements has been proposed following this line of research. Below, some of them are listed at Crypto 2020. Biller, Linder, and Todo provided a single bit distinguisher of 3.5 rounds and improved the attack on 7 rounds of Cha-Cha. In the last year, at Eurocrypto Day, Ito Future improved the attack on 7 rounds of Cha-Cha by introducing the concept of exploit key. And the same year, at Eurocrypto Continue, Ito proposed a differential linear distinguisher against 7 rounds of Cha-Cha by improving its linear patch. In the last year, Miyashita et al. Tried to give an attack beyond 7 rounds, and their attacks on 7.25 rounds of Cha-Cha take time complexity of 2 to the power 255.62 with a successful probability of half. However, as declared better, also this attack is less influence on than brute force. In short, since the first publication analysis of Cha-Cha in 2008, its validated target in the literature has stayed within 7 rounds. Finally, it's our attacks. Let's recall again the previous framework. For backward computation, one uses a function data G to approximation data I, which is corresponding to initialization. First, an observation is that the backward approximation can be seen as applied twice a single approximation in one initialization. As shown in this figure, the function data f is divided into double functions f. More precisely, assuming that the approximation data G is used in tag, which is made up of forward differential and backward approximation. By the observation, we can detect the new correlation with measure of about square root of the previous one, which take less amount of computation in practice. This practice is simple and was discovered in previous analysis. But it is surprising that it significantly simplifies the calculation of backward calculation. Next is about our new technique called syncopation. In the PNB-based approximation, the essential problem is how to find numerous PNBs with a large correlation. In the literature, the method for handling this problem are limited to a threshold rule and a gradient-like method. Both methods treat the cipher as a black box and don't exploit the AX struct cipher. Inspired by the partition technique, we introduced the technique called syncopation to exploit the properties of AX structure in the PNB-based attacks. To simplify the analysis, the part F is divided into 2 parts, F0 and F1, and G is a PNB-based approximation of F. The syncopation is used to the part G0 to CF0 to reduce its dependence on PNB so that the correlation between G0 and F0 is high. Here is a definition for describing the syncopation technique. Let y equal hx bn ax function for x and y if yo only depends on xo and the condition that a system or equation on xo is satisfied, then we call x sharp y sharp called syncopation beats, xo yo as the syncopated beats, and the beats io xo appearing in QR as restricted beats, and consecutive beats of each word is called a segment. Each segment of is syncopation beats is called a syncopation. The same to the syncopated beats called as a syncopated segment, and the pattern of syncopation and syncopated segment is called a syncopation property. Here is an example to illustrate the syncopation property. Please look at this picture consisting the operation of modular addition x is equals to s box plus key, where key is a word or secret key, and s is a public and known word. The blue lines represent for the syncopated beats and red line for restricted beats and the gray line for syncopation beats. In the word key, we set pin beats to syncopation beats and other beats to syncopated beats according to the syncopation technique, and the condition that the 15 beats of key is equal to the 15 beats of s, which are labeled by the right. Then we have that all the syncopated segment in x only depends on the syncopated segment of key and s, which are labeled by blue. As shown in the subfigure B, XO consisting to syncopated segment after remove two syncopation segments from X. To initialization, the property of syncopating property like differential and linear characteristics for AX separately provide the basic properties of modular addition and subtraction. Then we summarize their propagation of syncopation property, the same to the propagation of for X rotation and X over. Please refer the full version of our paper for details. With the tool of determining syncopated segment, we take the syncopation technique into account, and resulting PNBs are called conditional PNBs. CPNB for short. More precisely, by calling algorithm 1 in this paper, we obtain the syncopated segment and equations on restricted segments then, and the condition that all equations are satisfied, we estimated the backward correlation in experiments. The site of CPNB is constructed by selecting CPNB one by one. In each iteration, the key bits with the maximal conditional backward correlation is selected into set of CPNBs. An example on 7 rounds of cha-cha is given to demonstrate the effect of syncopation technique by algorithm 2. We got a set of 74 CPNBs and it's totally 27 segment syncopation segment and equations on restricted B. We remove the 13 essential equations from them, and the condition of the remaining equation are satisfied. The conditional backward correlation is estimated as by the experiments as 2 to the power minus 4.2, which is amplified over the 100 times than previous one. Next is a part for forward differential at the top of this page. It is a differential linear distinguisher used the attack to observe the given correlation after 3.5 round. Attack should generate a right pair for the given differential in the first round by analysis of the equation that controls the differential propagation, which are listed by at the bottom of this page, will achieve two improvements for forward differential. One is that we proposed a significant, consistent, efficient way to satisfy the given differential. This treatment led to a save time to -2 in the key recovery tag at the cost of 2 to the power of 4 times of data compared with the previous work. Compared with this technique, it doesn't require restriction on exploited key and save up to 2 to the power of 22 times of data. Another one is that a more comprehensive theoretical explanation is present for the strong key, which cover all the remaining 6 out of 8 cases, which like in the previous analysis. As applications, we present several attacks on different versions of Cha-Cha with 256 56-bit key, and some of them are listed in the table with a comparison with the best known attacks. Specifically for 7 rounds of Cha-Cha, 2 key recovery T are given. One is with a complexity of 2 to the power 210.3. Another one is launched with 10 and data complexity both less than the previous best known attacks. Towards the closing analysis of 8 rounds of Cha-Cha, we present 2 attacks against 7.5 or plus, which is defined as a version of 7.5 rounds of Cha-Cha without the last XOR and rotation. One of our attack is launched with a time complexity of 2 to the power 242.9. Finally, it's a summary of this talk. By the way, for the full version of this paper, please write for the following URL in print. In this paper, we study the security of analysis by PNB-based differential cryptanalysis. Specifically, proposed a syncopation technique and refined the key recovery with this technique. We improve the 7 and 6 rounds of Cha-Cha using the syncopation technique. Furthermore, several rounds on several attacks are presented on Cha-Cha 7.5 or plus. In a nutshell, we move a small but important step towards the analysis of Cha-Cha with the syncopation technology. For the future work, it is interesting and worth to consider how to apply the new technique on the other cipher, such as Salsa and Chasky. That's all. Thank you for your attention.
Thank you. Do we have any questions in the audience, in the room, or in Zoom? If you want to ask questions in Zoom, please ask them in the chat. Okay. When we're waiting for questions from the audience, I have one question. So this would be about the way you find the PNBs and the CPNBs. So you mentioned that you use the greedy algorithm. And I was wondering if we thought this could be perhaps automated using either MIAP or SAT sorting techniques, as it often happens in this kind of setting.
Yes, maybe automatic tool can help us to find more powerful distinguisher. For example, just as you said, you mentioned MRP-based or SAT-based tool. I think it is future work. Thank you. It's an interesting question.
Do you believe this could also improve your attack, or that the results that gave your greedy algorithm were actually like optimal in a sense?
Maybe but now there is there for the PNB based approximation, there is no such automatic tool, and there is a model MRP based to search distinguisher forward, and maybe in backward we need also this automatic tool, and it will improve our text. Thank you.
I see. Thank you. So I don't seem to have any question on Zoom, and let's see more questions in the room either. This is the last call. Otherwise, we can thank the speaker and also all the speakers of this session. Thank you. Next is the invited talk at 11:15. Thank you.
Okay.